I'm Nim, and welcome to my Physics Lab 3. So today the purpose of our experiment is going to be calculating the forces which will cause the motion of a star orbiting a black hole to not follow normal centripetal motion. So we're going to use a little bit of net force manipulation to find the mass of the black hole in question and the initial velocity and trajectory of a ship later which will fly near the black hole without crashing into our planet. So just a brief review of the results. The mass of the black hole ended up being 1.67 e to the 34th kilograms, and the initial speed of the spaceship was 1.06 e to the 7 meters per second. And then, like I said, we're going to do a lot of manipulation of Newton's second law and the momentum principle. So first, the fact that the final position is going to be the initial position plus the average velocity times delta t, and then similarly the velocity final is equal to the velocity initial plus F net over mass times delta t, and then knowing that F net perpendicular is equal to mv squared over r, the radius, times n hat. And then moving on to the universal law of gravitation, we have the formulas for those, and when we put those two formulas together, we end up getting gmr over distance squared, which we'll use a lot later during our code. In fact, all of these equations will come in handy later. And then just for some context, the system will be the star and the surroundings will be the black hole. Okay, so something else that's going to also come up in the future is assuming that F net is equal to Fg. This is because since our system is in space, normally when we think about our different forces of objects on Earth that we know, we always include negative mg because it is the gravitational force from the Earth. But in this one, we don't have that at all, and the only force is going to be the one from the gravitational force of the black hole. And so we're going to see in a little bit what the free body diagram is going to be, and it's going to show a little bit more of that. And just to talk about some initial conditions, our time is 0 seconds, our delta t is the amount of seconds in a day, the mass of the star is 2e to the 30th kilograms, and the gravitational constant is g, which we know. Okay, so here's our free body diagram. As you can see, the black circle in the middle is going to be our black hole, and then I'm just showing in this diagram that n hat is going from really large when it's near the black hole to really small later, and that's because n hat is very much influenced by the amount of gravitational force which is coming from the black hole. So as it moves away, n hat's going to be less tempted, while when it's really close, n hat just wants to run in there and point towards the center. And then p hat is going in the direction of momentum. So here's a video of what ended up happening in my code, like I said, with the arrows, and that's the magnitude of the force as the arrows are getting bigger. And then here's the coding. So first at the top we have the initial and final velocities, and then we move down to calculating the momentum principle. Then we do the changes in momentum and velocity, and we use that to calculate the force, which is dp dt. Then we're going to set that equal to the net force and find the change in p hat in order that we can find the parallel force and then find the perpendicular force, because we know that parallel plus perpendicular forces is going to be equal to F net. And then we can apply the gravitational force in order to get the answer that we're looking for, which is going to be in the results category. So we have F net parallel, F net perpendicular, and then the mass of the black hole, which is the most important part, which is 1.67 e to the 34th kilograms, I do believe. And then what does this even mean? So F perpendicular is the net force in the n hat direction, and then F parallel is the net force in the p hat direction that we saw in the free body diagram. And change in momentum is p final is equal to p initial plus F net times delta t. So momentum is taking all the forces, multiplying it by the change in time, and then adding it to the original momentum. And F net is taking all the forces and combining them. So they are different things. So like I said, F net doesn't, it's just adding the parallel and perpendicular, while momentum is multiplying both of those by delta t and adding it to the initial momentum. And next we're going to look at what if we want to enter an orbit around the black hole. And you can see the speed there, which the coding for that is right here. And basically everything from Newton's second law, all those equations are going to be manipulated in this coding. And then we will find the minimum initial speed for the spaceship to leave in order for it not to hit the planet or go into the black hole, obviously. And those are the results in the bottom right. And then going back to just our errors. So as I'm sure many of you realized while doing this experiment is that we had to do a lot of guessing and checking when it came to the equations and the numbers, which of course would result in inaccurate results. And also the computer quality while running the code and the examples was not always the best, so I also included that as an error. Thank you so much for watching. Bye.